In the previous lecture, we described the physics of the earliest phases of the universe from just after the Big Bang until the point that stars began to appear in the universe. It's now time to end this unit by looking at what happens at the other end of time. How does the universe end? What is the ultimate fate of everything? In a matter-dominated universe, the fate of the universe depends upon the matter density within it, parameterized in terms of the ratio of the total to critical density, omega naught. In a high-density universe, in which omega naught is greater than 1, the density exceeds the critical density for flatness, there is enough matter to slow, stop, and reverse the expansion. An omega naught greater than 1 universe in a matter-dominated universe would begin as a Big Bang, expand to a maximum size, and then the universe would stop, reverse, and recollapse again in a big crunch. It was as if the universe was returning to the original hot, initial, dense state that it emerged from at the beginning of the Big Bang. A Big Bang followed many billions of years later by a big crunch. In a low-density or flat universe with omega naught less than or equal to 1, the universe expands forever at a steadily decreasing rate. The universe ends in a big chill when everything reaches an ultimate, cold, dark, low-energy state. In a matter-dominated universe, density is destiny. You could go out and write this on a t-shirt and sell it. This is how the universe will end in a matter-dominated universe. High density, it will recollapse upon itself in a big crunch. Low density, it will expand forever, getting colder, thinner, and darker. A mass-energy inventory of the universe, however, finds that the total matter density is about omega matter equals 0.31. Broken down into components, starlight contributes only 1 part in 10 to the 4 of the matter density of the universe. Baryonic matter contributes about 4.8%, divided between 4.4% gas and 0.4% stars. Dark matter makes up 26% of the matter and energy density of the universe. All of these together, if the universe was matter-dominated, omega naught would equal omega matter would equal 0.31. Such a universe would expand forever at a steadily decreasing rate, getting thinner and colder and darker. But we don't live in a matter-dominated universe. We live in a universe with a non-zero cosmological constant, in which we see dark energy. If there is a non-zero cosmological constant, it adds to the overall mass energy density of the universe. Omega naught is now equal to omega matter plus omega lambda. In an omega matter-dominated universe, it would expand at a pretty much constant rate in round numbers. If omega naught lambda is greater than equal to 0, matter would act to slow the expansion, and the universe would slowly decelerate. If omega lambda was large, omega lambda would eventually, the dark energy would overwhelm the matter in the universe, and the universe's expansion would go faster in the future, slower in the past, and we would see an accelerating expansion. In the case of a non-matter-dominated universe in which there is a significant dark energy contribution, quantified as an omega lambda term, density is no longer destiny. Simply because you are above the critical density does not guarantee that you would necessarily recollapse in a big crunch. Dark energy could overwhelm even that and prevent the ultimate recollapse of the universe. Observations show that the expansion of the universe is indeed accelerating. Observations of distances for type 1a supernovae allow us to probe back into the earlier phases of the universe and show that the universe was expanding at a slower rate than it is today. The data are all consistent with an acceleration caused by an omega lambda term. When all of the measurements from the various techniques are put together, omega matter is approximately 0.31, omega lambda is about 0.69, and as a consequence, omega naught is equal to omega matter plus omega lambda comes out to about 1.0. This is consistent with various observations that the overall curvature of the universe on large scales is indistinguishable from being flat and Euclidean. As a consequence, the observations suggest that we live in a spatially flat, accelerating, infinite universe, a universe that will expand forever. Our universe is spatially flat and expanding at an ever-increasing, accelerating rate in the present epoch. As the universe expands, the rate of expansion will continue to increase, expanding faster and faster. The space between galaxy clusters will widen at an ever faster pace, and the temperature will drop at an ever-increasing rate. What is the ultimate fate of a universe which is spatially flat and expanding at an accelerated rate because of the importance of dark energy? We're going to now follow the proposed evolution of a universe spatially flat and accelerating rate of expansion, starting in the present epoch and moving forward as far as our physics can take it. We live in the present day in the Stelliferous Epoch, the star-bearing epoch, that began about 600,000 years after the beginning of the Big Bang. Today, the universe is about 13.8 billion years old. We are about 13 billion years, therefore, into the Stelliferous period. Most of the stars, especially the new stars that we see around us, are metal-rich. Each of these are in the process of making more and more metals through nucleosynthesis in their cores, and eventually the most massive of the nearby stars will go supernova and spread even more metals out into the surrounding interstellar medium. The next generation of stars to be born after the ones we see around us today will start out with less hydrogen and a lot more metals. Each generation of stars, more and more matter gets locked up in stellar remnants. Not all of the matter that passes through stars makes it back into the interstellar medium to form into new stars again. Low-mass stars to intermediate-mass stars will lock up some fraction of their mass, up to a maximum of about 1.4 times the mass of the Sun, as a white dwarf. Even of our own Sun will leave behind 45% of its mass as a white dwarf after it shuffles off most of the rest of its envelope at the end of its life. More massive stars will leave behind neutron stars and black holes, even though they blast off their envelopes as supernova remnants. There's always a net loss in the cycle of star formation. Every generation of stars that forms starts out with a little less hydrogen, a few more metals, but starts out with net less gas than before because some fraction of the gas every time around the cycle of star birth, life, and death leaves behind degenerate stellar remnants in which the mass is locked up, at least on cosmical timescales as we understand them today. Remember this as we move along into the deep history of the universe. We're going to see that locked up may not in fact be forever, if what you have to work with is a very, very long scale of time allowed by an infinite expanding universe. What is the fate of the universe? In many ways, we really want to know, what's the fate of us? What's the fate of the Earth and the Sun? Let's move history forward now from the present day, where we are today, and move forward in time. The Sun is presently about 4.55 billion years old and is getting steadily brighter, larger in radius, and hotter as it ages. This plot shown over here on the right shows the luminosity in blue, the radius in red, and the temperature in black of the Sun as it ages over time. Right now, the dashed line shows us where we are today at about 4.55 billion years old. We have, not surprisingly, one solar radius and one solar luminosity. That's our reference. In the distant past, the Sun was fainter and slightly smaller and a little bit cooler than it was in the present day. The reason for these changes is the slow change in the chemical composition of the core of the Sun as hydrogen is converted into helium for fusion, as we learned back in Unit 2. What's going to happen in the future? Well, as the helium begins to build up more and more inside the core, the Sun will rearrange its structure to accommodate the new composition in the very center, and the Sun will continue to get brighter, it will continue to get a little bit larger in size, and its temperature will get a little bit hotter, all of them moving together in lockstep. About 1.1 billion years from today, the Sun will be approximately 10% brighter. If we make the Sun 10% brighter in overall luminosity then here on the Earth, a moist greenhouse effect will kick into play. This will cause the surface temperature of the Earth to rise dramatically, beginning the slow process of beginning to evaporate away the oceans. It will become so hot on the surface of the Earth that it will effectively end all surface life. 3.2 billion years into the future from today, the sun will be 36% brighter. This will trigger a runaway greenhouse effect that will boil away the last of the oceans, evaporate away most of what is left of the atmosphere except the heaviest parts, and end all life on this planet, even that deep in the oceans, and perhaps even, except for maybe a few bacterial survivals, deep underground. Even this won't last for very long, because after a while, the sun will run out of hydrogen and helium after it's 10 billion years old, some 5.5 billion years in the future, at which point the sun will swell into a red giant and will begin the process of melting the outer crust of the Earth, and whatever crust was hiding in between the interstices of the crust will long since have vanished from the Earth. At the same time that the sun is swelling up into a red giant and baking the Earth, the Milky Way and Andromeda will continue their inexorable path closer and closer together, eventually colliding and merging into a giant elliptical galaxy, a process that will end as a settling down as a giant elliptical in the center of the local group, some 8 billion years from today. As we go further in time, the interactions among galaxies in the local group will move on, so by the time the universe is between 100 and 1,000 billion years old, the remaining local group galaxies will all have merged into one giant elliptical galaxy, where, in the present day, we see a relatively small and modest group of galaxies. 3 big spirals, a couple of irregulars, and about 50 or 60 small dwarf galaxies. A trillion years into the history of the universe, the local group will be gone, replaced by a single enormous elliptical galaxy. This may be the end of our history and the history of the Milky Way, but it's not the end of our story. We'll continue in the next part.